Hi guys, welcome back to Calculus. This is Mr. Robeson. Today we're going to look at putting everything together from Unit 3. So we're going to be graphing without using our calculator based on the function, the derivative, and the second derivative. We're going to take a look at the shape based on the derivatives, and we're going to look at an example here. And then the next video will just be 3 more examples. All right, so things we can find about a graph. Some of these things are from pre-calc, some of these things are from calculus. So X intercepts are when the y is 0, so we'd have a number, comma, 0, so we'd plug in 0 for y. Y intercepts is when x is 0, so we'd have 0, comma, a number, we'd plug in 0 for x. Symmetry, if we do f of a negative x, we'd get the same thing as f of x. That means it's even. In other words, it's symmetric. 2 m's. About the y-axis, like so this side would match this side. All right, if it's odd, if we plug in a negative x, we'll get negative f of x. That would be an odd function. And now the symmetry goes like this. So the first quadrant matches the third quadrant, and whatever's happening here will match whatever's happening here. All right, so the fourth and second quadrant match. All right, domain are the x values you can plug in, range are the y values you can get. Continuity, well, we look at jumps, we look at holes, we look for vertical asymptotes. Vertical asymptotes, again, are going to be x equals a number. That's how we write vertical asymptotes. We don't just write the number. The AP exam would mark it wrong if you just write the number. All right, so that's all stuff from pre-calc or earlier. We've now looked at relative extrema, so we've got maxes and mins. All right, we've looked at concavity, like concave up and concave down. We looked at points of inflection, so that's where it's changing from concave one way to concave the other way. And we looked at where functions are increasing, where functions are decreasing using the derivative. And we looked at horizontal asymptotes, the limit as x goes to infinity and as x goes to negative infinity. 2 different limits, and these will always be y equals some number. All right, so these are all things we've looked at from calculus. All right, so our guidelines here that we're going to follow is first we're going to get everything we can from the original function. So the original function tells us our intercepts, our domain, our vertical and horizontal asymptotes. Then we'll take the derivative and we'll find where it's increasing, where it's decreasing, and we can find relative extrema. And to do that, we would have to plug back into the original function. Then we're going to look at where it's concave up and concave down and any points of inflection by using the second derivative. Again, to get a point, we would have to plug back into the original function f of x. All right, and then we try and put it all together by graphing. So start with points. Start with points and asymptotes. All right, so any points you have on f of x, draw those. Any asymptotes you have, draw where those would be, and then just try and connect the dots using the increasing and decreasing, concave up and concave down. Skipped a slide. There we go. All right, so some things about shape. So if our function is increasing, so that means it's going up, and it's concave up, so that means it's, the U shape here. Well, increasing and concave up is this half of it over here. So it would look something like that. All right. If it's decreasing and concave up, well, that's the other half of it over here. So it's going to look like that. All right. Concave down, remember that's now our parabola opening down shape. So if it's concave down and increasing, that's this first half over here. The shape would look like that. And if it's concave down and decreasing, that's the other part of it over here. It's going to look like that. All right. So try and use those to put your graphs together. All right, so here is our first function. This is not a quick one. So we start with our intercepts. So if we want to find y-intercepts, usually the easiest thing to find, we have x equal to 0. We plug in 0. So f of 0 equals 2 times negative 9 over negative 4. The negatives are going to cancel out here. This 2 is going to cancel out with none of those. 9 over 2 is 4.5, so we've got a point, 0, 4.5. All right, to get the x-intercepts, and there could be more than one here. That's when y equals 0. We set the top of the function equal to 0. So we set 2 times x squared minus 9 equal to 0. Looks like we're going to get x equals plus or minus 3. So we get the points 3, 0 and negative 3, 0. Symmetry. So if we plug in, and we don't always have to do symmetry, guys. Sometimes it's nice, sometimes it's not nice. So if we plug in negative x, we could see what happens here. We get 2 times negative x squared minus 9 over negative x squared minus 4. Well, negative x squared is just x squared, so we get 2 times x squared minus 9. Same thing happens on the bottom. Negative x squared is just x squared, which is your original function. So that means it is an even function. Most of the time there won't be symmetry, but that means the left and right side match. So we're symmetric about the y-axis. All right, so that might help us with our graphing. Domain, so let's see. The only problem areas here is, well, the bottom can't equal 0. So we get x can't equal plus or minus 2. All right, so that's also our continuity issues, and that's also our vertical asymptotes. So we have a vertical asymptote at x equals 2 and x equals negative 2. All right, notice it's symmetric, so wherever it happens positively, it would also have to happen negatively. So that's what we're getting all from the original function. Next up, what are we getting from the derivative? So we need to find the derivative, f prime. To find the derivative of this, we're doing a quotient rule. All right, so that's low, x squared minus 4, d high, 2 is going to stay out front. Derivative of the inside here is just going to be 2x. If you want, you could distribute this and say this is 2x squared minus 18, and the derivative of that would be 4x right there, minus the top, 2 times x squared minus 9, times root of the bottom, which is just 2x, all over the bottom squared. All right, we can probably simplify that some because we're going to want to set it equal to 0 and factor and find where it's positive and negative. So let's see, we're getting 4x here. We can pull that out from both of them. We're going to be left with x squared minus 4 minus x squared minus negative 9, so plus 9, all over x squared minus 4 quantity squared. The x squareds here are going to cancel. That's nice. Negative 4 plus 9 is 5. 5 times 4x is going to be 20x over that whole bottom squared still. All right, we set this equal to 0 top and bottom. To get our critical values, we get x equals 0, and then x equals plus or minus 2. Our two asymptotes would always also be critical values. So now we're doing our number line chart with our first derivative with those three values in order. So we've got negative 2, we've got 0, we've got 2. Our factors are the 20x on top. I'm going to put the whole bottom together since it's squared. I'm not even going to bother to factor it. And when we put those sides together, that gets us the sign of f prime. So 20x, if we plug in a negative number for x, it's going to be negative. If we plug in a positive number for x, it's going to be positive. X squared minus 4 quantity squared. If we're squaring it in the end, it's going to be positive. Right? It could equal 0 at the lines here, but everywhere else it's positive. We put our signs together. A negative and a positive is a negative. Positive and a positive is a positive. So that means our function f of x is decreasing, decreasing, increasing, increasing. So right here at negative 2 is a vertical asymptote. Oops. Pause. And over at 2, we have another vertical asymptote. At 0, we're going to have a relative min. All right, so we got a point. We already actually have the point at 0. 0, 4.5 is a relative min. All right, so that's everything that we can get from the first derivative. So we got our increasing and decreasing, and we got our relative extrema. Now we want anything we can get from our second derivative. So we need to take another derivative of this guy right here. All right, so let's change the color one more time. Let's see if I can put this together. So now we know where it's increasing and decreasing to. So now we want f double prime of x. So we take in the derivative of this guy. We're doing a quotient rule again, so it's bottom. X squared minus 4 squared times root of the top, which is just 20, minus the top, times root of the bottom. We have to do a chain rule here, so we get 2. We leave the inside the same, to the 1 less exponent, times root of the inside, all over the bottom squared. The bottom was already squared, so that means it's going to be squared squared is to the 4th, like that. All right, so the bottom is always going to be positive, it looks like. Well, maybe not. We might be able to factor some stuff out and cancel it. So from the top, both of them have a 20, and both of them have an x squared minus 4 at least to the first power. So we can factor that out. So we get 20 x squared minus 4 to the first. And we're left with, from the first guy, x squared minus 4. All right, we took out the 20. We've got a 2, an x, and another 2x. So that's 4x squared all over x squared minus 4 to the 4th. Well, that 1 to the 4th is going to cancel out with one of those and leave us with it to the 3rd. So now it can change signs. So we get 20 times, let's see, we can combine some stuff. We've got negative 4 minus 3x squared. We can actually pull that negative out and just put it with the 20. That's going to make our lives a little easier. And on the bottom, we've got x squared minus 4 to the 3rd. All right, we're kind of running out of room here, but we want to know where that's positive and where that's negative. If we set the top equal to 0, the top's never going to equal 0. In fact, the top is always going to be negative because of that. This guy in here is always positive, times negative 20. Top's always negative. The bottom can change signs at plus or minus 2. Right, because this is cubed now. So it's going to take whatever sign this guy takes. All right, which we've actually, well, I guess we didn't already do that before. But let's just look at what's going to happen there. I know I'm kind of running out of room here, but I just need negative 2 and 2. And I'm just going to do the whole second derivative all at once. So the top is negative. If I plug in a number back here like negative 3, negative 3 squared is 9. 9 minus 4 is 5. 5 to the 3rd is positive. So the top's negative. The bottom's positive. The whole thing is negative. If I plug in 0, well, top's still going to be negative. Bottom's also going to be negative. So negative and a negative makes it positive. If I plug in positive 3, I'm going to get the same thing I got if I plugged in negative 3. So that means our F is concave down, concave up, concave down. All right, so now I know my concavity. We don't have any points of inflection because both of these were vertical asymptotes, so there's no points where it changes inflection. But it looks like, well, I need one more thing that I need to find that I skipped. It wasn't written over here. Horizontal asymptotes. So we're missing horizontal asymptotes. So I'm going to do that on the next slide. I think I have a room. Yep. So we want to take the limit. So these are for the horizontal asymptotes. We want to take the limit as x goes to infinity of 2x squared minus 9 over x squared minus 4. So the top, we really have 2x squared minus 18 over x squared minus 4. And we can really just compare the highest powers on top and bottom. And we're going to get 2x squared over x squared, or just 2. So we get y equals 2. The same thing happens as we go to negative infinity. We also get 2, so we get y equals 2. So as we go to negative infinity, we're going to 2. As we go to positive infinity, we're going to 2. Now we want to try and put this all together in one graph. So let's see. We're going to have 1, 2, negative 2 is a vertical asymptote. 1, 2, positive 2 is a vertical asymptote. And the way we draw in vertical asymptotes are just dotted lines straight up and down. Not so easy to line it up here with my little tablet. Let's see, what other things do we have? We've got horizontal asymptotes at 2 on both sides. So 1, 2, there's 2. So I don't need to put that in the middle, but as we go towards infinity, which is on the outsides, we definitely want to draw that. Let's see, what else did we have? We've got our vertical asymptotes, we've got our horizontal asymptotes. All right, let's go with some points now. So we got 3, 0, and negative 3, 0. And 0, 4.5. So 2, 3, 4, 5. So there's 0, 4.5. And we've got 3, 0, and negative 3, 0. All right, so those are points. Let's see, did we have any other points? Nope, don't think we had any other points. So that's this point, this point, this point. We've got both of those asymptotes. We know one side's going to match the other side. We're going to start off decreasing for the first two sections and then increasing. And we are concave down, up in the middle, and then down again. All right, so the middle part might be the easiest part to do. So we're concave up, we're decreasing, and we're coming from a vertical asymptote. All right, we got to hit that point, turn around, go back up. Kind of looks like a parabola, but both sides end up going straight up. All right, on the outside, we got to come from this horizontal asymptote. We got to be decreasing, so we're going to be right below it, and we're just going to be going. It doesn't even look like we're decreasing, but we are slightly. And then we hit that point, and then we keep decreasing for the vertical asymptote, like that. And then on the other side, we start off increasing, and we are concave down. So we're going to have this sort of shape. We're going to go from the asymptote, hit that point, to the other asymptote, like that. Let's see. I think I put a graph on here. There we go. Hey, that's pretty good. Not so bad. All right, so that was an example of how we put it all together. So we do our increasing, our decreasing, our concave up, our concave down, our original function values, and we put it all together in a graph. The next presentation is just going to be examples of practicing this. So please check out the next one for more practice.